plutonium in MIT. My PhD student as well. The objective of the presentation is just to show how to do steam gasification with solar energy. It seems to be quite easy, and a lot of trials has been done, and I will try to review and summarize some trials to show you how to do it, what are the challenges. But first, I will review a little bit steam gasification of biomass for those of you who don't know very well the technology, to see what's the reference, a non-solar case. Then we'll study how to provide a heat into the gasifier, which means different solar gasifiers that has been developed during the years to understand the trials. And then we will propose some new ways to do it, which are the currently trials that we are doing and studying at the modeling phase yet. Yes, first of all, just to contextualize the solar thermal energy into electricity or fuels, we know that the direct radiation from sunlight, it is taken from heliostat and to concentrate it, and then we can use in a, which is the point to put, So we can either go to electricity, which seems to be the normal way to do it in power plants, in solar power plants. But also we can use that heat to produce syngas, whereas syngas or hydrogen if we capture the CO2. And then we can synthesize fuels from that. So it's quite interesting, this route, instead of this one. Let's say this is the classical one. There are a lot of power stations, probably mainly in Spain, which is a leader country in thermal solar energy with about 50 plants. And but this route, of course, is quite interesting because we can increase the solar shares of the very fine product, chemicals or syngas. So we are trying to produce this in this presentation, but yeah. So something about steam gasification. Steam gasification is a well-known process, thermochemical process, and it's just, it's an endothermal process, and then we need heat. That's why it has sense to heat it with solar energy. Normally, that can be done in different ways. Here, we summarize conceptually the 3 ways. First, and the mostly used way, is to get with some steam and to add some oxygen, could be pure oxygen, and of course the feedstock, the biomass, or the fuel in general. And we produce a syngas, but that syngas has been used. It's not entirely the chemical energy from the fuel, but we have burned some part of the fuel. That is to maintain the process at the temperature, which is typically 900. Depending on the technology, but typically 900, let's say. But if there are some trials that they try to avoid to have the syngas contaminated with the CO2 from the combustion by trying to separate somehow gasification and combustion in different ways. I will not go to details, but then they produce syngas without the CO2, and the CO2 is here. They do this by, for example, dual fluidized. I will show you later because it's a reference case we will use to develop new technologies. But the most interesting, at least conceptually, case is to come up with the steam and the feedstock together and to get some solar heat, for example, external heat in general, solar in the context of this presentation, and to produce syngas. This way we have biomass and we have solar heat, we have 100% renewable. So we have the syngas with the energy from the biomass without any combustion. So everything 100% is here, and also we increase the share of the energy of the syngas with the solar energy. So that case is of course more interesting, but of course more difficult, that I will show you. Then this is just for you to know, the steam gasification, the stoichiometry of the process. We produce hydrogen and CO. In practice, of course, we have a syngas with many things. I will show you now. And but it can be it can be processed with steam into hydrogen and CO, syngas, or hydrogen, which means that we put 1 mole of steam more, and then we capture the CO, we react the CO with the water, and we produce CO2, which is actually the water gas shift reaction. It's a combination of two. In any case, we need this amount of water, whereas here we need this. Let's have a look here. This is the amount of energy that we need, kilojoules per kilogram of biomass. So we need a lot here if we produce syngas, whereas we need less if we produce hydrogen. So that is the energy that we need from the sun, typically. And we need typically this, in terms of kilograms, we have about 1/4 kilogram of steam per kilogram of biomass if we want to produce syngas, and typically 4 times more if we want to produce hydrogen. Yeah. This is, if we try to do pure allothermal steam gasification, it's just, as I showed you before, steam plus fuel, biomass, and we produce gas. This is the most interesting way to do it conceptually, not technically. And the heat can be enough and sufficiently high rate to produce at the thermal level of the gasifier. Recall that this is like 900, so we need very high temperature heat. It's not easy. Of course, we need concentrated solar energy. But as I told you, if we put biomass with steam together at this temperature, we don't produce only hydrogen and CO, but more things. Equilibrium calculations can be made, for example, with the stoichiometric steam, and we see that we need high temperature to get syngas. Otherwise, we have some solid carbon, and we also have CO2, and of course, we have converted steam, even methane, and other hydrocarbons. This is ideal thermodynamic calculation. The actual practice, we have even more things. But if we assume that thermodynamic calculations is achievable, so if we need, or we provide high enough residence time at the temperature, let's say here, we have this. And this is a representation of the heat that we need as a function of temperature. As I told you, here we should come up with syngas, so at this temperature we will need this, about 4 megajoule per kilogram of biomass. Recall that the biomass is about 18 megajoules per kilogram, so 1/4 is more is necessary to provide the heat, which means that the solar share, which is the energy in the gas, could be 1/4, like 25%. This is quite interesting because we have 125% of the energy of the biomass. The 25% is from the sun. That's quite interesting compared to the actual current process that they have typically 75%. Yeah, but how this can be done? First, non-solar version. The non-solar version is made in the actual practice by burning some char or burning some fuel. But to try to avoid to have a syngas with CO2, they separated gasification and combustor. And then, if you have a look here, we put the fuel here with steam, and then we gasify, we have the product gas. But we have some char and convert it. Recall that char is part of the fuel, and then we burn here to produce a flue gas. This material comes from the gasification to combustion, it heat it up, and then go back to the gasification to provide the necessary heat. So actually, the char combustion is given the heat here. Actually, if we see the dot line, the gasifier as a single gasifier, taking into account the 2 units, we just have some air and steam and fuel. But the main advantage of this is that we produce the product gas without the flue gas, without the CO2. And we are not using oxygen, we are using air, which is much cheaper. Yeah, this is what we have, and actually this is very well known for those working on the gasification field. The Gusin plant has been in operation during many years. I will not talk about the economy or the things. This is in Austria, and it's a dual fluidized bed to produce, in this case, is a CHP plant for production of electricity and heat. What about solar gasifiers? This is a jump because solar gasifier is actually at lab scale. Most of the trials has been tried to face the two main problems. One is to achieve continuous operation. We know that day and night is change, so the heat is not always possible. We know that thermal energy storage is possible to decouple somehow. We need some system, but yeah, this is one of the problems. And another big challenge is to try to make into contact the solar radiation with the biomass. And of course, from the thermal efficiency point of view, it's much more attractive to do it directly. So to illuminate, to re-radiate the reactor directly with the sun. But the problem is that, of course, it's changed with time, day and night, and it has to be controlled. And the materials and there are many problems. So it is a lot of development in train flow. These are, for example, two examples in fluidized bed and in train flow by direct irradiated reactors. Whereas in this case, these are indirect irradiated reactors, which have some intermediate surface to avoid the direct contact of the biomass with the use of windows, which is a main limitation because it's not easy to operate it and to maintain it clean. It seems to be stupid, but it's a very big challenge. So this has been developed to avoid the windows. So if we go from the left to the right, we decrease efficiency because here we have an intermediate surface, and here we have some heat transfer fluid which is used to indirectly irradiate and to come up with the heat and then contact, and it's another way. There are more ways like the molten salt, but I will not go to details. This is at lab scale, and there is nothing yet at commercial scale. But I will present a couple of new concepts based on this. What we try to do is not to directly irradiate the reactor, but to use a solar receiver, which is a stream of solid that is directly irradiated here. It could be, this is like the reactor, but actually it's not the reactor, but it's just to heat it up, the particles. We come to the hot bed storage, and then to the gasifier. Look at this. With this concept, we just have continuous flow of hot inerts, and we storage the materials. So the gasifier is continuously in continuous operation, day and night, without, it can be controlled somehow, but so that's the way. Of course, it's not directly irradiated, but today we are developing technology with solar particles receivers. So there is, the technologies are in the limit of the temperature that we need for biomass. For coals, we need a little bit higher, and it's a little bit more difficult. For those receivers, we use central powers, like the one in the picture. Actually, this is from a power plant, but the concept is the same. So how can we convert the dual fluidized bed, the non-solar, currently operated existing version of this, that one, into solar? So we have the hot, this is what everything except to the red lines are what I presented before. This is a dual fluidized bed, and this is with the solar. So we introduce the heat, and we extract the warm solid to go to the receiver. So this stream could be this one, and this stream could be this one. So in this way, we can operate it, but also we could try to imagine the perfect gasifier, which is in operation in this way, which is the more challenging because it's everything here, but it's possible to imagine that. I'm not sure how long. I have time, yeah.
Slightly more leisurely schedule.
All right.
That's good or bad is a
all right.
question.
let's have a look how to get this. We have made a calculation of how much hot solid from the receiver we need as a function of the difference of the temperature between the hot particle and the gasification reactor. So we need, of course, if we have more difference of temperature, which means we have the receiver higher temperature and a fixed gasification temperature, we need less material, but for the same heat. This is parameterized by different external heat. So this is all the heat that we need, so there is no air necessary, so we don't combust the biomass at all. Whereas if we are not so demanding and we want just to give some share of solar, for example, 25%, we just need that amount. Of course, we need much more solid circulation from the receiver if we want to put all the external heat in the solar form. In this case, this has been made. This is the solid circulation ratio, which is the ratio necessary between the reactors for a fixed temperature in the gasifier and in the combustor. And here you can see that this is the normal ratio. The ratio means kilogram of solids per kilogram of dry ash-free biomass. It is made on the basis of the biomass, which is the typical way to do it. And the reactor, non-solar reactor, works here about 30 kilograms per kilogram of biomass. And if we see that if we add more heat to the gasifier from solar, we can reduce the circulation till we have zero. Zero means that we have only a gasifier with hot solid coming here and out, and we don't need combust any part of the biomass. So here the process is more difficult till this is very challenging, but more interesting because we have the maximum share of solar in the syngas. And here we can see the necessary heat. Of course, if we go with more, if we add more solar heat, we need more kilojoules per kilogram of biomass. Yeah, here you can see this number. This number is what I calculated before based on equilibrium. In this case, it's calculated with the kinetic models. It's more realistic. I said about 4, and here is 3. Yeah. A second concept, that was to produce syngas, which is easier, but we can go even further. How? Just trying to have the two reactors. This is actually, there is a non-solar version of this, but it's in development, like many CCS processes, like oxycombustion, chemical looping, and so on. And this is could be called chemical looping gasification, or maybe enhanced gasification reforming, which is another name. But in this case, we can do with solar energy. Here, this is very simple. It's just to have the water gas shift and the CO2 capture in the gasification reactor. So when you want to produce hydrogen from gasification, you have to produce the gas, you have to produce the CO2 into CO2, the CO into CO2 to produce hydrogen from water, and then you have to capture the CO2. So in a big process, in a complicated process, in this case, we can do the three things together. This is not new, actually. This has been tried in the non-solar version. But in this case, we can do it with solar energy as well. I will not show, yes, this is for you to see how it operates at different temperature. And we have also a development. We are trying to develop this with the solar receiver, with the same concept as before. So in conclusion, steam gasification of biomass at industrial scale has only been developed using dual fluidized bed, meaning burning part of the biomass. Allothermal steam gasification is much more attractive because we can use all the chemical energy in the biomass into the syngas, but it's difficult to supply the heat to the reactor. So only trials at lab scale exist today. Calcium looping or calcium looping gasification is very attractive because we can put the CO2 capture in the gasifier, but there are other problems I have not mentioned, but like the activation of the calcium oxide, but also it's difficult to provide a heat. Solar gasifier is still at conceptual scale because they have tried to irradiate directly the gasifier. It's difficult, and promising results are envisioning, but with a lot of problems. So solid particles can make it possible to do it by decoupling the solar loop and the thermochemical loop. So we are working with several prototypes to try to envision how to do it for medium term, because the small devices developed up to now are very complicated. So we can do with existing technologies just by putting all the pieces together. So that is the main message of this presentation. Thank you very much.
Question or two?
Hey, good talk. So just to clarify, in traditional gasification, usually char is combusted to provide the heat to actually make the syngas.
In the dual fluid aspect, yes.
Right, and so you're by using solar, you have a higher yields because more carbon is pushed towards syngas. That's like one of the main advantages of using solar? Is that right? Just to clarify. Okay, that's it. Thanks.
This is, of course, desired because you are splitting water with carbon, which is a very attractive way to do it. From the solar perspective, they use the carbon to split the water. From the gasifier perspective, we use steam to oxidize the C into CO. So both things are together with that process. But it's, yeah.
Any other questions? Just wait a second. Let me give you the microphone so everyone can hear the question.
So I would like to know how the heat can be transferred inside the gasifier, indirect heating or direct heating?
In different ways. That is one of the challenging things. And in principle, yeah, this is details, but in principle, the most attractive way to do it is to use, if you think about, we have two loops. What the solar loop, which is carrying with the solid particles in a carton and the radiation, so it heats it up and then go to the gasifier. And in the gasifier, it has to be in the gasifier, in the combustor, and then going back to the loop. So if we do that, we only use one particle, yeah, and it's a direct mixing of particles. It's the same particle, so there is no indirect heat change. You get what I'm saying? Yeah, but you can, of course, use some heating medium to get the heat from the solid particles from the receiver and go to the reactor and then to transfer the heat, but then it's more complicated. You need more equipment, but it's a more conservative way to do it. But of course, if you do directly, it's much more effective from the thermal point of view, but there are other disadvantages. Like if you have some solid reactive material in the solid receiver, people developing the solid receiver are not thinking of that problem at the moment. One of the main messages I want to transfer is that we are using in developing things, but not very long. They are in the market almost. So I just want to use technologies. Of course, if I invent some receiver at 1200 Celsius, I can do much better things, but then I have to wait till my child do it, or my grandson, or whatever. So I want to do myself before die. That's the problem. They are developing a lot of solar gasifier, very effective, but small scale.
Okay, thank you.
Any other questions?
This is Friday evening. It's hard. I understand.
Yes, I'm amazed how many people are still here.
Yeah.
I apologize for my cynicism there.